Here's an example of a circuit where we're asked to find the equivalent resistance of the circuit to the left of terminals A and B. So we're looking to determine the input resistance looking in through those two terminals. Again, we note that the circuit is entirely composed of resistive elements, and there's only one slight, if you will call it a trick, in this, and that is the connection between these two nodes. This entire element is a short circuit, and it means that node alpha and node beta are exactly the same node. And so if you can recognize that, you'll find that the top of the 20 ohm resistor and the top of the 80 ohm resistor are connected together. The bottom of the 20 ohm resistor and the bottom of the 80 ohm resistor are connected together. And so therefore the 80 ohm resistor is in parallel with the 20 ohm resistor. Therefore the equivalent resistance of that combination is equal to 80 ohms multiplied by 20 ohms divided by 80 ohms plus 20 ohms. Working this out, top is 160, bottom is 100. This is 16 ohms. Alright, so we note first of all that the two resistors, the 80 ohm resistor and the 20 ohm resistor, are connected in parallel, and they have an equivalent of 16 ohms. Now we'll replace that by 16 ohms. If you look and see how the connections are joined together, you'll find that that's what it looks like. We'll replace that with 16 ohms. Once we replace that with 16 ohms, we recognize that the 16 ohm equivalent resistance and the 4 ohm resistance are connected in such a way that any current that flows through the 16 ohm resistor is exactly the same current as flows through the 4 ohm resistor. Therefore these are connected in series. The equivalent resistance of that series combination is the sum of the two, 16 ohms plus 4 ohms, total of 20 ohms. The 16 and 4 ohm resistors connected in series, total of 20 ohms. We'll draw it as it is, and we can see directly that the 5 ohm resistor and the 20 ohm resistor are connected in parallel. We find that whatever voltage is applied across the terminals of the 20 ohm resistor is exactly the same voltage that's applied across the terminals of the 5 ohm resistor. Therefore the two are in parallel, and we find that the equivalent resistance is equal to 5 ohms times 20 ohms divided by 5 ohms plus 20 ohms, which is equal 5 times 20 is 100, divided by 25, 4 ohms. And so therefore the equivalent resistance looking in through the terminals A and B is a total of 4 ohms. And we can demonstrate that by that equivalent circuit. And so this is our final answer. The equivalent resistance between terminals A and B is a 4 ohm resistor, and as far as the terminal properties are concerned, whatever happens to terminals A and B, a 4 ohm resistor is exactly the same as our original circuit, which was composed of a number of resistors in series and parallel. And so we can replace all of that with one single 4 ohm resistor.